Hi, this is Chirag Gupta, and I'm going to be presenting my recent paper on conformal prediction for predictive inference in regression problems. We develop a new method called Cube for quantile out-of-bag ensemble methods. This is joint work with Arun Kumar Kuchibotla and my advisor Aditya Ramdas. Conformal prediction is a framework for predictive inference developed by Wolf and collaborators. In this talk, we focus on the regression setting, but conformal can be used for any prediction problem. So in the regression setting, suppose we have samples from a distribution over X and Y, and a scatter plot for the distribution is denoted by the blue points on the left. You don't have to care too much about the precise form of the distribution, but this is the true form in case you want to regenerate our results. Now, predictive inference refers to the problem of providing not just a mean estimate for Y, but actually a prediction set C such that the probability of Y being in the set C is at least 1 minus alpha. And alpha here is some small threshold such as 0.05, 0.1, etc. And this is called a 1 minus alpha prediction set. However, you may notice that C of x can be some very large set, such as C of x could be minus 1 comma 4, and it would satisfy this guarantee for any alpha. And thus, we want to provide predictive inference and prediction sets such that the expected value of C of x is small, which means that on average, the length of the intervals that we provide are small. So on the left, the red prediction bands denote the optimal prediction set, which is the shortest prediction set, which has the 1 minus alpha coverage guarantee for alpha equal to 0.1. So this is a 90% prediction set. And the green refers to the cube prediction set, which is the prediction set provided by our algorithm. And you can notice that without making any distributional assumptions, cube still provides very nice prediction sets, which are quite short on average. In our work, we reformulate conformal in a way that is intuitive and universal. This framework can be understood even if you are unfamiliar with conformal. We now describe step 1 of this framework, which starts with a family of nested intervals. First, we want to define a sequence of nested intervals that reflect some belief regarding the form of y given x. This is best explained through the following example. Suppose we believe that y given x is normally distributed with some mean and variance which is unknown. Then we can consider the following family of sets for varying values of t corresponding to some mu hat and sigma hat, which are some estimates of the mean and variance. The intuition is that if mu and sigma were known perfectly, then this family contains the optimal prediction set. Similarly, suppose that we believe that y given x is non-negative with a mode at 0. Then we can consider a family of sets corresponding to the interval 0, q hat tx, where q hat is a quantile estimate. Again, if q hat was known perfectly, this family would contain the optimal set, which is 0, q hat 0.9x. In general, a nested family is defined as shown. So you have left endpoints and right endpoints given by L and U, and these are parameterized by some t. So the t corresponds to the family. And if you take 2 points A and B in T, such that A is less equal B, then you want that LA UA is a subset of LB UB. So this corresponds to the nestedness assumption. Now there are two things to be learned: the nested family, which is L and U, as well as the particular value of T, which corresponds to the particular prediction set that we will return. And this is where we use conformal to learn this in a distribution-free and valid manner. So step 2 corresponds to learning the parameters L and U, and step 3 corresponds to learning T. We illustrate these through a simple example, which is conformal based on sample splitting, also called split conformal. Consider the nested sets corresponding to symmetric intervals around the mean. So it's mu hat x plus minus t. This is just one illustrative example, and in general, you can consider any family of nested sets. The first thing we do is we split the data, and on split 1, we learn a mu hat, an estimate of expected value of y given x, which is mu hat, using any regression algorithm. And on split 2, we perform calibration to learn the value of t. So let's say the split is given by this d, which is n data points. On these endpoints, we compute the residual of yi with respect to the nested family, formally defined as the minimum value of t such that y belongs to this family of, belongs to the particular set. So mu hat plus minus t is a huge family, and you want to uh, find out the smallest value of t such that yi actually belongs to this set. And this is called a residual or a non-conformity score, because if yi is very far away from mu hat, then the residual is high, or in some sense yi is non-conforming with respect to the training data that mu hat was learned on. In this particular case, you can notice that the Ri is actually equal to the absolute value of yi minus mu hat xi. However, although it's very simple in this particular case, we can consider more complex families of nested sets where it may not be straightforward to write down Ri in this form, and that's where our framework is most useful. The next thing we do is we learn a value of t corresponding to the 1 minus alpha quantile of the residuals R1 through Rn. And this corresponds to our conformal. So this t hat gives us a conformal guarantee of the following form. The probability of y belonging to mu hat x plus minus t is at least 1 minus alpha. This probability is marginal over d as well as the test point, and not conditional over the calibration point. So this guarantee is available in a distribution-free manner, no matter what the assumptions or the distribution of the underlying data is. And it's kind of surprising that this guarantee can even be provided in such a way. The next thing we do is we use the nested framework to develop a more nuanced conformal method, Cube, that achieves competitive performance on standard UCI datasets using 4 key ideas, and we'll go over each of them in the next couple of slides. But first, I'll describe the guarantee provided by Cube. So unlike split conformal, which provided a 1 minus alpha coverage guarantee, Cube provides a 1 minus 2 alpha coverage guarantee. So we lose a small factor of 2. However, in practice, we always obtain 1 minus alpha coverage. So in some sense, this is a lower bound, whereas in practice, we always obtain 1 minus alpha coverage. We will now describe the first 3 ideas of Cube, which is quantile regression forests with out-of-bag predictions. The first idea is to target quantile regressor-based nested sets instead of mean regressor-based nested sets, as given by this family. Instead of mu hat plus minus t, you have q hat alpha over 2 minus t and q hat 1 minus alpha over 2 plus t. And the motivation is that if the distribution was unimodal and symmetric, then the optimal prediction set or the shortest prediction set would belong to this family. Now to perform quantile regression, we use an ensemble technique, quantile regression forests, developed by Meinhausen. However, we wish to avoid sample splitting and use all the data while training to maintain sample efficiency. And for this, we want to do this while maintaining coverage validity. And for this, we rely on out-of-bag prediction. So suppose the first 4 data points go to tree A, and then data points 2, 5, 7 go to tree B, and so on. Then the out-of-bag trees for the first data point corresponds to tree B and tree D. Similarly, the out-of-bag trees for the second data point corresponds to tree C, and so on. And hence, we can now define a separate out-of-bag predictor for each data point. So q hat minus 1 corresponds to a quantile regression forest with just the trees B and D, and so on for q hat minus 2 till q hat minus 7. And hence, we have multiple non-conformity scoring functions R minus I. And these can be aggregated using cross-conformal, which is our next idea. So that's cross-conformal aggregation. And cross-conformal aggregation is like leave one out cross-validation or jackknife, but it's a provable way to combine predictions, which leads to distribution-free coverage guarantee at level 1 minus 2 alpha, as I described earlier. We'll not go through the details of cross-conformal in this short talk, but I encourage you to read our paper or talk to us in the discussion session to learn more. So this is a link to our paper, and you can also find the Cube code on my GitHub repository. and I hope to see you at the discussion session. Thank you.